Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
Alrighty, everybody. Welcome to Back to the Basics Concurrency. My name is Mike. Wonderful to see everybody in person or online or in the future on YouTube. Thanks for taking the time to join this session here. All right, so there's the abstract that hopefully drew you into this talk. That's what we're going to be talking about. And the code for this talk is available online. So I'll show this link again at the end. There will be samples. Most of the samples have lots of comments. I apologize if they're hard to read on the slides a little bit, but you can always look at the samples as of right now. Who am I? Again, Mike Shah, and primarily I teach these days, but I also do consulting as a senior 3D graphics engineer. Love doing that, and you can read more about that on my website. And what you're going to learn today, so the foundations of concurrency. Again, from a beginner's standpoint, this is the Back to Basics track. But ideally, you're someone who wants to learn a little bit about some of the fundamental building blocks for writing multi-threaded programs. We'll look at threads as one of the examples of concurrency. We'll look at some others as well with asynchronous programming. And I want to hopefully help show you some of the foundations so that you can pick some of the correct higher level constructs or the right abstractions to build your concurrent programming. And concurrency itself is a massive topic, so I do want to start from the beginning. And this talk really is going to contain two core components. I want to start with the motivation and sort of the why and make sure that that's very clear for why we write concurrent code and write matters. Then I'm going to have several sort of toy examples where we can learn from and you can take and apply as needed to your code. Okay, and then hopefully at the end there will also be enough resources that when you're ready to do a deep dive or build a really big multi-threaded system or highly concurrent system, you'll have at least a few pointers where to go from here. So let's start from the beginning again. What is concurrency? And again, the motivation here. And in a way, I like to start this off from just human psychology, just thinking about how I work concurrently, balance work, family, to-do lists, all my half-finished C++ projects and different hobbies and so on. But the reality is our brains are, as humans, we're really good at focusing on one task at a time. If you get too many, things get difficult. I can't code and listen to music, for instance, which is, kind of a bummer. But luckily, computers can do things concurrently. We just have to tell them how. But typically when we write software, we sort of think about it in this sequential way, right? One instruction after the other when we're writing our code. And I can abstract this just a little bit more to have these, instead of instructions, think about them as one function executing right after the other. So here's just a visualization of a call stack. Again, main calling the foo function, then we call the bar function, which calls another function, and so on. So, we could have a second path in our code executing as well. We could be doing things concurrently. Again, we have nice machines with multiple cores. We'll talk about that. So we should get our money's worth and put our computers to use. So if I have two threads, that means twice the performance, right? So that sounds great. So yeah, let's go ahead and learn a little bit more about that. And one of the things I think about is this sort of idea that performance is the currency of computing. It's a really nice phrase, and I can't take credit for it. There's wisdom beyond me here. But this is from Charles Lyserson, so maybe you've read his book or seen him at MIT, but he says you can often buy needed properties of software with performance. So concurrency is one way that we can get improved performance in our software and do neat things, whether that means better graphics, more responsive, more of something, or more efficient usage of some resource. So how do we get more performance? What are our tools going to be? And that goes back to our original question, what is concurrency? So just to sort of get one or two terms correct here, because concurrency is often interchanged with parallelism, but they're different things when we study them in computer science. Concurrency means we have multiple things can happen at once, the order often matters, and sometimes tasks have to wait on a shared resource. Parallelism, on the other hand, means everything happens instantaneously, all at once, or roughly. So just focusing on the concurrent part, since we're talking about concurrency for the majority of this talk, again, the order matters. Sometimes tasks have to wait on shared resources. Okay. There's a really nice comic by the late Joe Armstrong sort of illustrating this idea of what the difference is between concurrent and parallel in the real world. So I've got one coffee machine here. Concurrently, two lines have formed here, so multiple tasks are going on. These people can be on their phones or waiting, but only access to one shared resource here, the coffee machine. Whereas parallelism is two coffee machines, two coffees at a time. Okay, so that's a difference. That's one way I like to think about concurrency versus parallelism. Okay, and concurrency and parallelism, implemented correctly, should yield better performance in most cases. Okay, but beyond performance too, sometimes there's just a necessity to concurrency. How we model some problem. Okay, so just again to give some real world examples, just to make really clear concurrency, I like to think of an orchestra, a subway system, cars at a traffic stop, and those will be some of the analogies that I described. But to bring this back to computer science, sometimes we think about a memory allocator. That's something where we're sharing resources, memory, and maybe we can hand out memory concurrently or multiple chunks of memory at a time, but we have to think about it. How do we sort of organize that? Our file input outputs, network requests, where we're maybe waiting on data, but we could be doing something else. These are some things that we want to think about. And again, concurrency is largely going to be motivating us from a performance perspective. At least that's how I'm approaching it today. So again, concurrency, as heard in music, just to make the analogies really clear, ideally all the instruments aren't playing at once, or you don't go to an orchestra where nobody's playing. Probably not a good concert to be at. So there is some synchronization going on amongst the different folks playing. Okay, if you want to think about this at CppCon when you're out to dinner, good concurrency is sort of like a good conversation, right? People are talking back and forth. Maybe not everybody at once. Again, not nobody speaking. But there are some shared resources you have to share here. Different food and so on. Each person might be competing for those resources at some level. So we do have some things, some structure that we have to keep in mind when we think about concurrency here. So, the question is, does our hardware support concurrency? Well, the answer is yes, but I need to give you a little brief architecture history here. This is the classic, every concurrency talk needs a slide of Moore's law, a rule. But on the x-axis, we have the years. On the y-axis, we have the transistor count. So again, Moore's law, roughly every 18 to 24 months, we're doubling transistor count here. Okay, and this chart is going as far as 2020, and that's largely true today. We'll talk about why it's still true. The rules bent a little bit, but this is largely true. The reality is, though, as far as getting more transistors on a single CPU, that has largely been abandoned in most, the machines that are probably in front of you today as far as your laptop. There's a lot of heat as you start packing things more densely together. Then you try to, run your system faster, maybe overclocking it, and that generates more heat, more power demands, which is not linear. And also, we're going to talk about this issue of memory speeds being able to keep up, and if it even makes sense to make the CPU run faster. So Herb Sutter has a really nice article written many years ago at this point called "The Free Lunch is Over." Again, motivating why we need to change how we think about programming in a sense and learn how to become concurrent programmers. Okay, and Dennard Scaling is the other term. So often I'll see Moore's law in a slideshow, but I won't see Dennard Scaling, which actually talks about the increase in power consumption and the amount of heat that chips are generating. That's one of the major problems. We can keep shrinking things. My understanding is we still have a long way to go as far as how many transistors we can put on a chip, but it's the heat and the power draw. Okay, so the hardware industry, is going to adapt here in a way to keep Moore's law, as I say, accurate, or this trend of doubling of transistors. Okay, so now we have more CPUs or more cores on our actual machines. Okay, so we just add more cores rather than packing more transistors onto a single core. So again, does our hardware support concurrency? Well, yeah. So our cores are going to be able to work on separate tasks if we have multiple, or even one CPU core being able to perform multiple tasks. Just some quick examples I'm going to flip through just to show this trend. Since I like gaming, right? Xbox, 8 cores. Xbox Series X, 8 cores, right? More cores. PlayStation 5, if you can get a hand on one, 8 cores. More cores. That's a general trend in architecture, right? This goes back to the 60s, 70s. This isn't a new idea to add more cores to try to get some more concurrency or some more level of multitasking on your machine. All right, so we've got our sort of motivation and some of the core ideas. So, now is it time to just start coding? Well, almost. Let's first see what our mechanism is for doing the concurrent programming. Okay, so our mechanism is something called a thread. This is our tool as a programmer, one of our tools of many for doing concurrency. It's not the only one, but it's the one I'm going to focus on primarily today. So what a thread allows us to do is have 2 control flows at the same time. So we'll have sort of a main thread, which is illustrated on the left of the figure, and a thread on the right here. It has its own logical control flow, so you can see that different functions that are highlighted in green here, this second box and this third box, are executing different pieces of code. Now threads are going to share the same code base, or the sort of program space where our code is, as well as some of the data on our program. Okay, so threads, you may have heard of them in this other term that they're a lightweight process. So it's like having multiple processes on a machine, but threads are working together within one process. So again, just another figure to make this sort of clear, the higher level view of a thread. We have one process, right? When you double click an application or run it from your terminal, but that process can have multiple threads of execution within it. Each of these threads, again, is sharing the same code data in the kernel context. That's all the stuff here on the right here. So when you allocate memory on the heap, for instance, that's shared. All the libraries that have been loaded in, and so on. Threads, however, have their own thread ID. That's how we know which thread is unique and how it's executing. And it has its own logical control flow, so which line of code, if you want to think about it that way, that it's executing. And then a thread has its own stack for local variables, however. So the locals available in a thread so that's this stack 2 and stack 1 here, are separate. Now, if you're being really crafty, you could access the different variables, but that might be a little bit dangerous. But ideally, threads have their own local storage. Okay, and that's what they have that's unique to them. Okay, so when should we be using threads? Well, threads generally come in handy when you're doing some sort of heavy computation. So the most sort of obvious example these days is in graphics cards for graphics programming. You have a lot of operations for filling in pixels or doing tasks in parallel in this way. So that's what our GPUs are really good at, launching different threads, hundreds or even thousands of threads on a GPU on your machine. One other use case, though, beyond just computation, though, to think about is, threads are also a way to separate the different work that we need to do in our programs. So again, it might be for performance, but sometimes it's just a logical way to separate the different tasks that you're doing on your machine. It makes sense to break a task and split up the work, right? We sort of do this algorithmically sometimes when we do recursion or breaking down a problem. A thread's another way to break a task up. Okay, so let's look at threads in modern C++ in the standard thread library. So we're going to be looking at the C++ standard thread library. This is a library that I personally recommend for folks as far as portability. So whether you're using G++, Visual Studio, Clang, the different compilers are more likely to be supporting the features from 11 through 20 or 23 coming in a few years. There are other libraries. Boost has a threading library. Intel's thread building blocks, pthreads, if you've done Unix programming, are available. And the reality is std thread might be built on top of those. I know for my Unix system, I'm linking in the pthread library when I show the examples. But using the standard thread library gets us all on the same page. It's good for portability unless your domain has a specific need for something else. Okay, so here's what you get with the standard thread library in C++. We get threads, JThreads we'll talk about, and then there's some other ways to manage or control what your threads are doing. Put them to sleep or make threads wait for something to happen, sort of the idea of yielding. All right, so let's go ahead and look at a first thread example here. And essentially what this example is going to be showing is something that's similar to fork join parallelism, if you've learned about this in C, where we have a process and we spawn some other tasks that takes place. Okay, so what I'm going to be doing here at line 14 is creating my first thread here. And what it's doing is it's executing the printout statements here in this function here. So I'm creating my thread, and it's starting a separate logical flow of execution, or if you want to think of just launching a function that has its own control flow, starting with test and passing in 100 as the argument for x. Okay? And when I do that, here's the result. I compile. Again, I'm linking in the pthread library, and I get hello from thread, argument passed in 100. Those were the two print statements in test. And then way down here, I get hello from my main thread. So if I wind back down to line 21 here, I'm getting hello from my main thread. Now there's one thing I didn't talk about here, which is at this line here, 18, mythread.join. And what join does is it essentially says, hey, as soon as I create this other thread, it's going to go off and do some work. It's got its own logical flow of execution, its own task that it's concerned with doing. That starts from this function here. But what join's doing then is saying, well, I was called here from my main thread, so main thread, please wait for me until I finish my work. And that's a way that we get synchronization amongst different threads. Okay, if we didn't have that, otherwise our main would just execute, return 0, terminate, and maybe there would be this other thread sort of hanging out. Likely our program's going to crash, but that's what happens. Okay, so that's a lot in words to sort of consume what's going on in the example. So I want to, again, illustrate it in a picture, what's going on in this, our Hello World threads program. So just visualizing the execution of hello thread. So where does it all begin? Well, same as all of our other C++ programs from the main function. So we have one main thread at this point, we can think of it. And then we're going to march down and begin constructing our thread here, my thread. So here it is. And well, in the construction of the thread, we're calling the test function. Okay, I'm passing in the address of test so that we call the test function. And then we can have a variable number of arguments here. Okay, so here we are. We're about to begin our new thread. It'll start executing as soon as the construction finishes here. All right, so again, it's its own logical flow of execution here, my thread. And then at this point, both of our threads are executing concurrently. So we've made it this far. We've written our first concurrent program in this sense. Okay, now what happens next is a little bit arbitrary as far as which thread executes next, maybe at the same time on different processors. But let's just say that this line of code happens to execute next, the join. Okay, so join was this other construct where it says, hey, my thread is requesting, or stronger than it requested, saying, hey, main, you have to wait here until I finish. Okay, so we'll just put a little wait sign there, and it's got to wait for lines 7, 8, 9, and 10 to finish executing here. Okay, so my thread here is going to continue executing, printing out the cout statements, and then it'll eventually return. When we return from a thread, that's one way that we're terminating a thread and saying, hey, we're done with that execution, clean up the thread, and continue forward. Now at this point, we're rejoining back with our thread when we terminate. So some signal is being sent here. And then we can continue executing down through line 21, hello from the main thread, and finish our program. Okay, so here's the same example before, but this time with a Lambda, just to change things up a little bit. So that's what's highlighted here in the orange box, and here's how I'm calling it. Same exact example. All I'm showing is that a thread here can be created with some sort of callable. So whether that's the address of a function, a Lambda, or something else, that's another way that we can initiate or launch a thread. All right, so that's pretty cool if we can launch one thread, but what if we want 10? Because we want to start doing some more serious work here. So in this example, I'm going to launch 10 threads. And I'm going to do this from a loop here. So I've still got my Lambda here. That's where I'm doing my work. And it's just going to print out the thread ID. So that's something a little bit new. So std : this underscore thread get ID. That's how we'll know which thread's actually executing. It's some sort of identifier. And then the argument passed in. Okay, so whatever x happens to be. So here at line 15, I have a vector of threads. So I can sort of collect all of my threads in one place. So that's what I'm going to do in this loop here, looping through 10 items, pushing in each of the threads that I create. And then I'm going to join the threads here. Okay. Now let's go ahead and execute this. So again, I'm creating each of our threads and joining them. And here we go. Now this is a little bit subtle, and I'm wondering, do folks who I can see here in the audience, do they like this? I see a no, head shaking. Because what I've essentially done is I've made my program very sequential here. Okay, we can actually see it. This could happen, but it's unlikely that I'm going to get the first thread with the argument of 0, 1, 2, 3, 4, 5, 6 happen in that order. It's possible. That has to be a possibility. But something's sort of fishy. And it has to do with, again, as soon as I create this thread, and if I join it right away, that means wait. Okay, so we think, or I thought I was a concurrent programmer here, but I'm just writing sequential programs that are really slow now. So this result seems a little bit strange, and folks see the problem here. Excellent. Okay, so we can't join immediately in this manner. So if I want to launch a bunch of threads, this could be a typical recipe. Right, so what I've modified here is lines 17 to 19. I just push in the threads, and then I have a second loop that's joining the threads. So as soon as I create the thread, I can execute, do some work, and then I'll join them after. Maybe they're close to terminating. It doesn't really matter, but we have to wait here in our main for all of our threads now. And you can actually see in the execution order here, the first time I ran this, that you're getting a different ordering of your threads here. Okay, now this can be a little bit troublesome in a way because, well, we have to create a thread and then we also have to join a thread. That's two things to sort of keep track of in our mind. And as I add more things that I have to keep track of, that can be a little bit tricky. So C++20 has added a feature. It's called JThread. And that'll launch a thread and join the thread immediately. But it has the effect of when I run this program here, it's not going to make it sequential. It is going to join it to the main thread, but it can execute. Yeah, question?
No, join immediately is not the right term.
Join immediately is not the right term.
Join when the destructor of the thread is called.
Yes, yeah, thank you. Join when the destructor is called. Yeah, so the comment was JThread doesn't, we don't want to confuse it with join thread. Thank you. It's join when the thread is, the destructor is called. Thank you. Good catch. Catch me if I'm off on, especially on the new stuff.
So in your example, the join happens at the end of the name.
Yes. So to repeat, where the or trivia or question for the audience, where is it going to happen? Where is this thread actually going to be destroyed? Well, when it leaves scope here, which is at the main, that's when the destructor is called. Yeah, thank you. Okay, so we can launch a bunch of threads here, but how can we get them working together, working with data? Okay, because printing out stuff's interesting, but let's actually work on some data. Let's crank things up 1,000 threads working together. And we can talk if this is actually going to give us performance or not, but let's forget that. Let's launch 1,000 threads. Let's say I have a really strong system here. And maybe we want to do some task where each of the threads are counting the size of files in a directory, for instance. That might be something reasonable to do. Okay, you can sort of break up the work and imagine how we might do that. I'm going to simplify things a little bit, or part of the task, and I'm just going to have a shared value to sum up the total. Okay, so let's see what that looks like. So similar example, I'm back to just using our regular threads and joining them, but I'm launching 1,000 threads, joining them, and the work that those threads are going to do is call this function, increment underscore shared underscore value, which is a global variable. Yeah, globals are a little bit ugly here, but we need somewhere where we can share or write to a common location. Okay, so each of these threads is going to increment or add 1 to the shared value. And here's the result. So I ran this a couple of times, and I said, yeah, the logic seems fine. This is how I would do it in a sequential program. And maybe that's where I start from. But we're getting a different result here. It's not deterministic because we're getting 998s. Oh, the right answer, 1,000, 1,000, and then a bunch of other different results. So 2 out of 6 probably isn't a good, batting average for our program here. So why does this happen? Well, this brings us to some of the pitfalls of concurrent programming and what we have to think about. And specifically with threads here, data races, starvation, and deadlock. So I want to talk about this. And the problem, what we have here, is I have, at least one thread here and then n, so in our example, 1,000 threads. And they're all accessing this shared value at the same time. So some of them are reading from shared value, and they're saying, okay, this is the value of shared value, and then they're going to attempt to write to it, which means add +1. And another thread simultaneously, while that write is happening in another thread, is reading the old or previous value. Okay, so we get this sort of weird interleaving. The classic example is sort of the bank account where you ask yourself, what happens if I deposit $50 in my account and withdraw 50 at the same time? You should end up with 0. That shouldn't be dependent on the order that you do the transactions or if something happens in between. Okay, so we're getting an interleaving of instructions here. Let me just go back where I have I have to read the shared value and then write or update it with +1, while another thread is also accessing this shared value. Okay. All right, so this is what we call a data race, where the result that we're getting in our program is related to the order of execution, and we don't have some deterministic way to get the same result. So what we can do is use something called a lock to protect our data. So just like you use a lock to protect something or allow only one person to enter your home, we have locks in programming. That's one of our mechanisms. In C++, a lock or a standard lock is what's known as a mutex. And it allows mutually exclusive access to a block of code. Okay, so we sort of think about this as an atomic operation here. What it does is we're able to protect a line or a series of lines of code where only one thread can access that block of code. Okay, so again, the analogy, think about having exactly one key to your home. You always carry the key with you. Only one person who has the key can access the house. When the person enters, they lock the door so nobody else can get in. You can do whatever you want in the house. And then when you leave, though, you have to pass the key on to somebody else. The next neighbor or the next thread who's knocking to get in. Okay, so how do we fix this in C++? Well, we have a Mutex library here. And I've added 4 new lines. So the library here, Mutex, a global lock here, so that we can lock and unlock. Just think about this as our one key that we can enter into the house. And then with that lock, we can call .lock and .unlock. Okay, and that's effectively protecting what's at line 14 here, that shared value. Okay, only one thread can enter at this point. And the other threads have to wait, even if they're waiting right before line 13, before they do something. Okay, and this is the result. This looks better to me. I ran it 5 times. Maybe I should run it 500 or maybe more, but this is correct. So again, this idea of mutual exclusion, just to illustrate it, to make it a little bit more clear, what we've added here with our lock here is, we're protecting this code here between the lock and unlock. And we give that a name. Usually it's the critical section, critical region, but it's some code where we're guaranteed, at least in this example, that only one thread at a time is going to enter here in our mutex. Okay, so here's the illustration. Again, if you can imagine one of the threads having the key here, it can access our critical section, and all the other threads are blocked. Okay, so they have to wait. They're just sort of knocking at the door every once in a while to see if they can access or obtain the lock. So what happens if the lock is never returned? This is equivalent to, taking the key in the house and being the one person, then you flush it down the toilet and then you just stay there, right? Does anybody think this could be bad? Yeah, get some head shakes in this direction. Yeah, this is bad. And we have a name for this. This is called deadlock. So it's a lack of any progress for a thread. Our threads, in a sense, looking at our example here, I've commented out line 15 where I don't return that lock. I never unlock the door. So effectively, as was mentioned, when our thread executes and then it terminates, right, it destroys its destructor, it's taken the lock with it. It holds the ownership of this lock and then it's gone. Okay, so this is going to crash your program. If you're lucky, you'll get a crash. In a deadlock, your program will probably just hang and no progress, at least for a portion of the program, or in this case, the entire program will be made. Okay, so how do we fix deadlock? Okay, so if we're just maybe trying to reason through this to start, well, we can rerun our code and we can sort of inspect and say, okay, for every lock that I have, do I have an unlock? And you can sort of like match the pairs. They can say, okay, maybe my IDE has some tools, these sort of static analysis tools, and I'll mention some of those at the end. But otherwise, it has to be sort of carefully detected at runtime and fixed. This is another case where, as our code gets really big, don't think toy examples, but thousands of lines or millions of lines, these can be hard to find. Okay, so we want to be careful with std mutex even. So it has solved the problem in the sense that we're protecting this shared value here, and our program is correct. But what if a programmer comes and updates this code and they're going to do something a little bit more wild here? And they said, okay, we need to update our code so that we handle exceptions within our code. And we say, okay, that seems like a good idea. Our code's going to be exception safe here. So we add a try block here. Some more code. It's within our critical section. This is great. And we're updating the value, but then we throw some exception. Okay, so maybe something happened in this code that was strange here. And then when we catch that exception, we decide the safest thing is to abort. Okay, this is effectively doing the same thing where we're terminating the thread here. So the exception's thrown, our program terminates, and we lost the lock. right? It's been thrown in the garbage disposal or the toilets again. But we do have a better tool here. This is, so starting in C++ 11, if you have access to 11 in your code base, we can use something called a lock guard. And a lock guard will take care of releasing the lock for us. So let me draw your attention to the lines between 13 and 16 here, where I have, or just on the line 16, the lock guard. It's a lock guard for a mutex, and it takes ownership of our global lock here. And then this lock guard, regardless if we're doing something strange like throwing an exception and then maybe terminating, or if we're just leaving scope, it'll take care of returning that lock for us. Okay, so regardless of the exception or if we leave scope here. So we like this. It's only one line of code. I didn't have to remember to lock or unlock or keep track of things. And it also handles that weird case, if I have an exception or something weird that happens. Okay, so you'll actually see in the run of the program, every time it throws the exception, but we still eventually get our value here. So that works here. So LockGuard itself is relatively simple. It's got a constructor, a destructor, and then a not copy assignable. So basically, this is taking advantage of our resource acquisition is initialization, or RAII, which you'll hear that term, right? This is going to construct, take ownership, and when it's destroyed, we will leave the scope here. Now, if you're able to use C++ 17, so you've got a newer code base or newer compilers available, you can use a scope lock. It's very similar to LockGuard, right? If we look at the member functions and what's available, but we're allowed to have several mutexes here. Okay, so this simplifies things a little bit if we're using multiple locks in our code, and again, able to use these RAII principles. So again, if you have a newer code base, probably prefer scoped lock here. Okay, now in this actual example where we're counting things, there's probably a better tool for this. If you're just trying to keep track of things or count them and make sure that your programs are safe. And in C++ 11 and beyond, we have stood atomic here. And what are atomics? Well, they work on generally primitive types or any type that can be trivially copyable, meaning you just have a set of bits that can sort of be copied. This has to do a little bit about how the hardware is going to implement atomics. But let me show an example, maybe just to make it clear how to refactor our program with 1,000 threads with an atomic. And what I've got here, again, I'm going to draw your attention to the picture here, but this time I've got, again, it's our global, it's shared value, but we've got stood atomic and then the type here, int. And then when I increment the shared value here, notice I'm just doing shared underscore value plus plus. Because of this type, when I modify this value, it's already protected. Now that mechanism might be a lock, it might be no lock, okay? But there is some hardware way to protect and ensure that we're not reading and writing to this value amongst multiple threads, okay? So we like this if we are just counting things, for instance, or using plain old data structure types. A brief aside for this on C++ 11, if you're initializing something with static, that is thread safe. It's worth mentioning. If you want to read about it, you can read about it on the CPP reference website. And this intuitively makes sense that you don't have to sort of put locks everywhere. We don't want to sort of make our code very littered, but we don't need to. It's guaranteed that when we create a static variable, it'll be initialized once in a thread safe manner.
That's a static global? For the thread local variables, you don't need that.
Correct. So the question was, this is a static global, right? So for the thread local, since they have their own thread local storage, correct? Yes.
No, that is about static global.
Static local to a function. Yeah. Let me. So if I'm doing in a a member function and creating this static, yeah, I won't have a race condition with that when I'm constructing it.
Static global or only constructed once?
Static global is only constructed once. Correct, yeah, because when we're creating our program, right, it has to be statically allocated. Does that clear everybody's questions? Yeah.
I think so.
Yeah.
I think maybe the words on the screen are the same. I'm not sure.
It says static local variable.
On static local variable here. Yeah. All right, so another primitive that we have is something called a condition variable. So we've been looking at locks, but and these are a little bit strange when I first started working with them. Even the name might be a little bit peculiar, but there's some condition on some variable that needs to occur. So let me give you maybe a practical example just to see what condition variable means. So if I'm given two threads, say we have a worker and some reporter here. Okay, so the worker is going to do some work, update a value somewhere, and then the reporter is going to say, okay, I'll print out what that value is. The condition variable allows us to, in a sense, take one thread off the queue and have it just sort of wait until it's received a result. Okay, it'll get notified, a sort of flag will be waved and said, okay, I've got my result. The analogy folks like to use with this is if you go in the States, if you have a post box, a little flag will be put up so it notifies you that there's mail and you should go check your mailbox. Okay. So in this example, just to walk through it, I know it's a little bit tiny, but I've got a thread reporter here. And the key is it's got this if not notified. And notified is just some Boolean value, just a regular bool variable. Okay, and then I've got this other line, G conditional variable dot wait on this lock here. Okay, so it's going to wait and don't do anything until we've been notified that we can proceed in this reporter thread. And then we'll have a second worker thread that's actually going to do the work, and it's responsible for sending that, or about really updating that notified value. Okay, this is the postman or postwoman raising the flag and saying your mail is here. Okay, so it changes notified to true, and then the important part at line 42 is G condition variable dot notify one. So it's going to notify one of the threads that's waiting on this conditional variable that, yep, the work's been completed, so you may proceed. Okay, so it'll look something like this if you run through or look at the code example. You have a main, it starts when the work is complete, which is the responsibility of the worker thread to report. The reporter can report on the result here, which was just setting an integer value. Okay, so there was another mechanism here that was introduced, something called a unique lock here. And this has been since C++11. And it's a bit more powerful than a lock guard or a scope guard. I mean, we can sort of just infer this by looking at what member functions are available here. And it's going to be what's necessary for this condition variable. Because we are able to, if we look at the locking functionalities, lock and unlock. And we can also sort of try to lock or obtain ownership over some lock, okay? So we need this, something a little bit more powerful than, again, our lock guard or our scoped lock. Still follows the same RAII principle, so we do like this. Okay, and at this point, there's several other primitives that you might want to look at the different types of locks here. I can't cover all of them, but I think looking at these first ones is a good place to start, and these are good ones to start using. Again, something better than just plain mutex is what we want to look for. Okay, so a quick recap of the C++ that we've learned here. A lot in a little bit of time, but we've learned about threads, JThread, mutex, lock guards, condition variables, atomics, and two things to worry about in our programming. So data races, that's why we're going through the trouble of using some of these locks, and then deadlocks, which is lack of any progress programming. All right, so getting to our original motivation here, now that we know some of the primitives here about performance and showing how concurrency can help us. And an interesting performance thing to think about is how we're often bottlenecked by input-output, or I/O, whether that's reading from a disk or reading from network. The reality is our processors, while they're not getting exponentially faster, say every year in terms of clock speeds and some of these things, our memory is more of a linear trend as far as the speed ups that we're getting here. So we need to think about how can we get a lot of our data onto our processors so that we can operate on that data. Okay, this is a kind of fundamental trade-off here for performance. So one of our tools might be to think about asynchronous programming. And this is another sort of form of concurrency where execution, again, can happen independently of the main program flow. And it's happening, asynchronous means A, the sort of first letter without synchrony, okay? So without ordering in some sense, right? We can have a separate flow of execution. So I want to introduce a few ideas also introduced into C++11. This idea of async, the keyword here, and then promise and future. So here's a tiny example utilizing some of these. I'll draw your attention to line 14, where I have auto here. This is going to create for my async function. This is a future. I've got it in the comment above. And then we're setting equal to this async term that we've just learned here. And async is going to spawn some other thread of execution here with square and the value of 12. So it's going to compute 12 times 12 here somewhere. And let's assume some time passes, and at line 16, we'll want to get that result from whatever this computation was here that's stored or that we created here at line 14. Okay, and that result of whatever this asynchronous function computed, we can retrieve with .get. So if that value is available, we will retrieve it. If it's not available, we'll block on our program and we'll essentially just wait here at line 16 until we can make further progress. Okay? So that's the idea with async and future and promise. Yeah, question?
Line 16, it doesn't mean that you are synchronous with program.
Yeah, so the question was at line 16, somebody is bothered that we're synchronized here, right? Or we're waiting here, right? We are blocked.
Yeah, actually, my question is that you are not asynchronous, but calling the get function means that we want to synchronize our code.
Right, so the concern is, again, in this example, that this is essentially a sequential program here, right? I just want to introduce async, future, and a promise. Let me move to one slide forward and see if it gets a little bit better here. When in doubt, add more code and complicate things. Okay, so let me give a more concrete example to this, right? Where we're really concerned about where we might get blocked on I/O. In this example, yeah, why not just call the square function, right? That would be the right thing to do here. This is over-engineered. It's a good toy example to learn this stuff, but it's over-engineered. But one area where we might want to think about this, again, where we're thinking about input-output, or we often have to wait to load data. If you go on YouTube, or for example, you notice the data that's been loaded when you're watching a video, and some of it that's getting buffered up or loaded over time, right? So there's got to be some sort of maybe background thread that's loading up or processing this data asynchronously here. Okay, so here's my asynchronous I/O simulation here, and we'll see if this is better here. Are we, the question I think to understand the concern is, are we able to do two things at once? That's better for performance, right? And are we blocked anywhere in this example? So let's keep an eye out for that and see if that's a problem here. Okay, so what this example is here is sort of a mocked version of an async thread where we're trying to load some data over time, right? Maybe it's for a video player or something. We're going to spawn a background thread using std async. And then in our main loop, we're going to continue executing our program, but we're going to keep querying to see, hey, has that function returned? Does it have the data we need? And there could be many ways to do it. We could wait for all the data or some of the data. But let me walk us through what I've done here. So just by starting out here, let's create our asynchronous function. This time I've been incredibly verbose writing out the types here just so you can see them. So we'll create this background thread asynchronously. And I've also got this other thing here at line 25 where I can check the status of my future here, meaning have I completed my work? There could be, have I completed, what are the other results? I want to see if our result is ready. Okay, that's eventually what I'm going to hold here. Okay, so in our, if we want to think about this as a worker thread or a background thread, I've got this function here called buffered file loading here. Okay, and our goal here is just to read bytes from a file. Okay, I've simplified things here. I've just got a counter here for the bytes loaded, and we're going to load, 20,000 bytes here. And I've a few artificial sleeps here to make it interesting when you run this. But this is going to be running in its own thread. It's got its own while loop, its own execution here. And in our main loop, we're going to check every 1 millisecond while we're doing other work. So I've got a line here at line 28. The main thread is running. And see if our result has come in. Now, we don't want to block. So there's no .get here anywhere, because that would be a blocking operation, right? So instead, what we're just going to do at line 35 through 37 is say, OK, the status is our future is ready. Then print out the data is ready. OK, and then we'll just terminate our program in this toy example. But you might want to do something else, launch another system, start playing the video, or whatever your domain is. OK, so I'm going to show the animation here. I compile it. I run it, and what I want you to observe until you can, really look at the slides close is there's two different things printing: main thread running and loading file. Okay, the main thread running was printing out some information, and then our background thread was printing out information. So that is happening concurrently. Okay, and then this program eventually does terminate. So the very bottom left corner, we will eventually see data is ready, and then move through our execution here. Okay. So this could be one of the use cases here. All right, some other odds and ends bringing us towards the finale here, a sort of rapid fire section of topics not covered. Again, right, I want to push folks forward after this. Thread sanitizers. So these are helpful tools for figuring out, did I write a concurrent program that executes without deadlock, data races? You can catch some of those concurrency violations. Proving that we have a program that has none of those, can we do that? Something I think about halting problem and some of these things, but so it can't catch all the errors, but it can help us catch some of them. So performance-wise, I haven't touched on this, but launching 1,000 or 10,000 threads doesn't magically make your program 10,000 times faster. Right? There are certain, maybe if you're talking about threads on a GPU, maybe that's true for the graphics portion. If I'm talking about threads on our CPU, a general rule of thumb I've heard is 2 threads per core you have can accelerate. We haven't touched on other things like sharing data amongst threads and false sharing and some of these other issues, but I want to just give you those key terms: true sharing, false sharing, that may be performance hiccups if you think you're using threads properly, but your program's slowing down. In C++ 20, we're getting, we have coroutines. So that's another way to sort of collaboratively execute, not write your code, but execute your code. I need to think a little bit more about them before I present them, but it is a way for you to launch some execution in a separate area, sort of yield and save your state, and then continue execution elsewhere. Right? So this sort of way to cooperatively work in your program. Now, what's enabled a lot of this thread or the stood thread package, which we've talked about, is that C++ has a memory model. Okay, that's going to define things like what order the reads and the writes happen. If today's your first time looking at threads, or you haven't tried out some of the examples, this probably isn't the place to start, but this probably is the way to look at or read through the C++ memory model and the standard and just understand where some of the newer primitives are coming from, how they're implemented, and why they work, and sort of convince ourselves why they work. Some common concurrency patterns, again, just giving you the key terms so you know maybe how to implement or some exercises to try. The reader-writers problem. So this idea, if you have a bunch of threads reading from a location, a bunch of other threads writing, how do you synchronize that? We actually have some really nice examples actually in the shared mutex page about how to do this. So there is something called a shared mutex, which allows multiple threads to read a value. And that sort of makes sense with what we've learned today. We could have a million threads reading the same value as long as they're not updating it, right? That seems okay. That is certainly okay. So there's a nice example about that to think about what you're doing with your threads. The other popular concurrency patterns, producer-consumer, where you have some producer thread generating some data, maybe putting it on a queue, and then a consumer thread grabbing data. Okay, that's another great one to implement. Barrier is another pattern where we might want to allow multiple threads to access a critical section. Right? That's sort of like if you think about going to a stadium or a sporting event or even this room where there's a fire code where we're allowed to have 30 people in this room, but once we get more than 30, we have to block. Okay, and that's what a barrier allows us to do. So there's some tools, counting semaphores, and latches and barriers that can be helpful in C++ 20. All right, some brief notes on parallelism in 30 seconds or so. Sometimes you don't have to do any work, right? Your hardware is pretty good. So there's sort of the implicit type of parallelism, CPU pipelining and some of these ideas where you just get the parallelism for free. So you don't have to worry about that. That's on the hardware. But you do have your explicit parallelism. So for folks who are going to go on and do GPU stuff and work with threads on a GPU, or maybe CPU parallelism with SIMD instructions, that's something to consider as well. Graphics is the domain to be thinking about parallelism as well. And there is the standard par and par unsec libraries. I would direct you to some of the other experts on that. So here's 2 talks to think about the parallel algorithms that are in the C++ standard library. So Bryce's talk has a lot on the implementation notes, and Dietmar's on a lot of usages on how to get started. All right, so some conclusions and further resources as we race towards the finish line here, and a few analogies on teaching. It's useful to talk about Amdahl's law if you're teaching this and thinking about, in the first place, do you have opportunities for concurrency? So Amdahl's sort of one way to think about how much performance you can get. We talked about data races when we have contention amongst 2 entities here, 2 threads in this case. Some other examples, it's not always as obvious. There's sort of a famous milk problem that has origins back to the 80s. If you want to think about you and roommates getting milk and leaving for the store and how a data race might occur, I'll leave that there. Thinking about starvation in terms of if you've ever been stuck at an intersection and not able to proceed. And then we have talked about deadlock, which is a very extreme case of starvation where you can't make any progress, right? This sort of gridlock here. All right, so it takes a little bit more care to do concurrent programming with some of these caveats that we have in mind. Okay, and I've showed some good toy examples, I hope, that can get you started with some other layers of abstraction, the things like the lock guard, scope guard, and so on that I hope are going to be useful. So some further resources as promised for getting started, some more talks, and where to sort of look for puzzles or places to practice in concurrency. All right, so we need concurrency for performance, and often it's a nicer way to structure our program depending on the problem that we're trying to solve. I think the async loader one is hinting towards that. Okay, both performance and the structure of our program. All All right, so with that, thank you everyone for your time, for the questions. I'm going to stick around and I'll take your questions now if we have however much time. Thank you. Yeah, question.
Waiting for the text to join, isn't it like sequential programming?
Pardon, I didn't hear.
When we create threads and we wait for the text to join,
Yep.
aren't we doing the similar sequential thing? Like how is it?
Yes. So the question is, when we create threads and we're waiting for them to join, are we just creating a sequential execution? And the answer to that is yes. If we create a thread and we join right away, then we're essentially doing sequential execution, right? That's no different than almost just making a function call, right? But if we create our threads, let them go do work, and then join later, that's how we're able to get some concurrency. So I can run to one of our previous examples, I think, where we were doing the counters. Let me go to the launching 10 threads example here. So this was where we had the sequential execution, where we were just joining right away. So this was bad. And then this is how we fixed it here. Make sense? A quick question?
When you do asynchronous programming, you have to, at some point, you have to synchronize. You have to get things back together.
Yeah, so the comment was, when we do asynchronous programming, we have to eventually synchronize and get things back together. Yeah, absolutely. We do have to do a .get to retrieve the value in our asynchronous. Right? We have to wrap everything up before we just terminate the program. Right? All of our threads need to finish. I'll hang around for other questions, sessions over, but I'll take your questions right after. Thank you.